Hi everyone and welcome to this second lesson on binomial probability distribution. In the previous lesson I would have laid the foundations for understanding the binomial probability distribution, and we were looking at this problem where we also calculated the probability that x is equal to 0. Again, we were told that suppose that only 35% of drivers come to a complete stop at an intersection having flashing red lights in all directions when no other cars are visible. What is the probability that none of the 7 randomly sampled cars coming to an intersection under these conditions would A, none come to a stop, B, at least one come to a stop? We worked out the probability that none would come to a stop already, having derived the parameters for the computations, which is P, the probability that a car would come to a stop would be 35% or 0.35. Q was equal to 1 minus P, which is 1 minus 0.35. P is the probability of success, which is the probability of the outcome of interest to the researcher occurring, which is 35% chance that a car would come to a complete stop at an intersection, while Q is the probability of failure, which is the probability that cars would not come to a complete stop at the intersection, which is simply 1 minus P, which is 1 minus 0.35, which is 0.65. And the sample size, which is the number of cars included in this experiment, is 7, as stated here. So these parameters must always be defined before you even start to attempt the computation of the binomial probabilities. So in part B here, we're asked to find the probability that at least one car would come to a complete stop at the intersection. Let us rewrite the probability formula for binomial probabilities. It's the probability that x is equal to x is equal to n Cx, or we could use NCR, either is fine, multiplied by p raised to the power of x multiplied by q raised to the power of n minus x. Now in this case, we're asked to find the probability that at least one car would come to a stop at the intersection. So there are really two ways of doing this. So this is the probability that x is greater than or equal to 1. That is the probability. That is what at least 1 means. At least 1 means greater than or equal to 1. So what we're interested in here is the probability that at least one car would come to a complete stop at this intersection. So this is the probability that x is greater than or equal to 1. The long way to do this would be to calculate the probability that x is equal to 1, the probability that x is equal to 2, the probability that x is equal to 3, straight up to the probability that x is equal to 7, which is the full sample space, because a random sample of 7 cars were chosen. But that's very lengthy and indeed tedious, time consuming. So the easy way to do this is to use the principles and laws of probability. And one of the most fundamental of those laws is that the total probability is always equal to 1. That is, if I worked out the probability that none of the cars would come to a stop, plus the probability that one would come to a stop, plus the probability that 2 would come to a stop, straight up to the probability that all 7 cars would come to a stop, if I worked out those probabilities individually and added them, then I must get the total probability of 1. So using the premise that the total probability of all possible outcomes, including the outcome of 0, there is the chance that none of the cars would come to a complete stop. There's also the chance that one car would come to a complete stop, or that 2 or 3 or 4 or 5 or 6 or 7 cars would come to a complete stop. If I worked out the probability of each of those possible outcomes individually and then added up those results, I would get the total probability of 1. So the easy way to do this problem is to simply write that the probability that x is greater than or equal to 1 would be equal to 1 minus the probability that x is equal to any value to the left of 1. Since you're interested in the probability that x is 1 or more, which is what greater than or equal to 1 means, then if I knew the probability of the events before 1, which is only 0, then I could just subtract that figure, probability that x is equal to 0, from the total probability of 1, and it would give me the probability of all the events from 1 to 7. And so that's the easy way to do this. So this will be 1 minus, we already know the probability that x is equal to 0, which is 0.049. That's what we calculated here, 0.049. And then when we subtract 0.049 from 1, it's going to give us the probability that 1 or more cars, which is at least 1, that's what at least 1 means, 1 or more. It will give us the probability that at least 1 car would come to a stop at this intersection. So the answer here is going to be 0.951, or if we convert this to a percentage by multiplying it by 100, it will be 95.10%. So there's a 95.10% chance that at least 1, in other words, that 1 or more cars would come to a complete stop at the intersection, which seems pretty practical in real life. Now let's look at number 3, and let's first again write the probability formula for calculating probability on the binomial distribution situations. So we write the probability that large x equals small x, or you could have used x equal r, these are just merely symbols, is equal to ncx, which is n combinations of x, which we can derive easily from our calculator by looking for ncx or ncr, some calculators may have ncr, multiplied by p, which is the probability of success, multiplied by q, which is the probability of failure, raised to the power of n minus 1, n minus x. And I want to remind us that the probability of success is just the probability that the outcome that you or the question or the researcher is interested in occurs. Doesn't mean a literal success, and failure does not mean a literal failure. So q is the probability of failure, which just means the probability that the outcome that you are not interested in computing for actually occurs. So here we're asked to find the probability that exactly 3 cars will come to a stop at this intersection, a complete stop at the intersection. So this will be the probability that x is equal to 3, because x here represents whatever we're calculating the probability for. So the probability that x is equal to 3 would simply be this. N, which is 7, we know that n is 7, which is the total sample size taken for the experiment. So it will be 7c3. So you can go to your calculator and just use NCR or NCX, depending on which one your calculator has, to work that out. So you would just, for example, click on your calculator 7, then NCR, and then select 3, and then the equal sign, and it gives you the answer. Or you could work out all of this at once in your calculator, meaning NCX times p to the x times q to the n minus x. You can do that all at once in your calculator as well, and that's fine. So we're multiplying by p, which we know p is 0.35, raised to the power of x. Again, x is whatever we're calculating the probability for. So this will be 0.35 raised to the power of 3, because we're calculating the probability that 3 cars, exactly 3 cars, would come to a complete stop. So therefore we know that the power here, x, is 3, multiplied by q, where q is 0.65. Always remember that p plus q must add to a power of 1. So it will be 0.65 raised to the power of n minus x, where recall that n is 7 and x is the value for which we're calculating the probability, which is 3. Then we simplify this. 7c3, again, you can just easily derive that from your calculator. So deriving that from your calculator, for example, I can use the online calculator 7C3, and 7C3 is going to give you 35. It can also be computed manually as previously indicated. So 7C3 gives us 35. So 7C3 is 35 multiplied by, now we're going to say 0.35 raised to the power of 3. So you just say 0.35 raised to the power of 3, which again you can get that easily from your calculator. 0.35 raised to the power of 3, which means you're multiplying 0.35 by itself 3 times. Or you can use the x to the y or the hat, the symbol on your calculator to do it, or some calculators may have an x to the y. These are what you use on your calculators to raise the powers. So 0.35 raised to the third power will give us 0.0429 rounded to the third decimal place. Again, the more decimal places you use with the binomial probability distribution problems, or in general really in mathematics, the more accurate your results are. So with binomial distribution problems, it's recommended to use 3 decimal places. So we'll get 35 multiplied by 0.0429 using 3 decimal places. Then we're going to multiply it by 0.65 raised to the power of 7 minus 2. Because 7 minus 2 is 5, then this is just 0.65 raised, 7 minus 3 is what we're using, not 7 minus 2, this is 7 minus 3. So 0.65 raised to the power of 4, which is going to give us 0.179. Okay, this is 3 right here. Let's just write that a little bit more clearly so it doesn't confuse anyone like it did with me just now. So this is 7 minus 3, not 2, because x is indeed 3. And 7 minus 3 gives 4, so then we raise 0.65 to the power of 4, and we get 0.179 to the third decimal place, when rounded to the third decimal place. Now when we multiply out all of these, which is 35 multiplied by 0.0429, and when we multiply out all of this, this was rounded to the fourth decimal place, so that's fine. So when we multiply 35 by 0.0429 multiplied by 0.179, we get an answer of 0.27 rounded to the 0.269 rather, rounded to the third decimal place. So this will be 0.269 or roughly 26.9%. So there's a 26.9 or almost 27% chance that exactly 3 cars will come to a complete stop at this intersection. And so that's how we calculate binomial probability. Now the next question says, how many of the 7 drivers do you expect to come to a complete stop? And what is the variance and standard deviation? So in effect, the first part of the question here is asking us for the expected value or mean. On average, how many of the next 7 cars would you expect to come to a stop? When we are finding the expected value or mean for a binomial probability distribution, we write E of x, which is the expected value of x, is equal to n minus p. N times p, rather. N times p, or simply np, where n would be the number of trials or the sample size, which is 7, multiplied by p, which is the probability of success, which is 0.35. So np is how we calculate the expected value or mean of a binomial probability distribution. So when we multiply 7 by 0.35, we get 2.45. But because the binomial distribution is a discrete probability distribution function, which really means that there can only be whole number outcomes. In this case, we can't have 2.45 cars stopping at the intersection, but we could have 2 cars stopping at the intersection. So this is almost midway between 2 and 3, so we would expect between 2 and 3 cars, 2 to 3 cars, to be coming to a stop at the intersection. In practice, that is how we would interpret something like this, because 2.45 is almost midway between 2 and 3. Would more likely be expecting 2 cars, because the 2.45 is closer to 2 than it is to 3. So we'd more likely be expecting 2 cars to come to a complete stop. But the possibility exists that on average we could also have up to 3 cars coming to a stop at this intersection. So that is the expected value. We expect most likely 2 cars to come to a complete stop at this intersection, but 2 to 3 cars is, in general, what we would expect to come to a complete stop at this intersection. So the expected value, or mean, for a binomial distribution is always found by multiplying n, the sample size, by p, the probability of success. And to find the variance, var of x, for a binomial probability distribution, we simply multiply n by p by q. So npq is how we find the variance for a binomial probability distribution. So n is 7 multiplied by p, which is 0.35, multiplied by q, which is 0.65. And this is how we'll find the variance for a binomial probability distribution. Any binomial probability distribution, you're going to multiply n, the number of trials, by p, the probability of success, which we would have defined earlier, and which I recommend you first define before you start attempting your binomial distribution problems. So this will be 7 multiplied by 0.35 multiplied by 0.65, which gives us 1.593. It's 1.593 rounding to 3 decimal places. So this is our variance, and I'm going to say therefore. So these 3 dots here means therefore. Therefore, my standard deviation would simply be the square root of the variance. Always and everywhere, the standard deviation for a discrete probability distribution function, such as the binomial probability distribution function, is simply the square root of the variance. So the standard deviation of x here, standard shortened deviation of x, is equal to the square root of 1.593. So to find the standard deviation, you're always going to take the square root of the variance. And when we take the square root of the variance of 1.593 here, the square root of 1.593, which is going to give us our standard deviation, the square root of 1.5, square root 1.593 is going to give us 1.26. That's 1.26, which, if we round this to the nearest whole number, it's going to be 1. So 1.26 is much closer to 1. And the interpretation of the standard deviation is, on average, what level of variation or deviation do we expect each observation or outcome to have from the mean of that data set? So because we're dealing with a discrete probability distribution function, then we round this to the nearest whole number, which is 1, because it is very close to 1. Much closer to 1 than it would be to 2. So on average, we expect there to be a deviation or variation of 1 from the actual mean of this data set. So it is possible that on a given day, the number of cars arriving at the data set could in fact be more than 2 or less than 2, or more than the mean or less than the mean, because of the existence of a standard deviation here that is different from 0. So this is how we calculate the standard deviation here. And this is how we compute probabilities for the binomial probability distribution. And this is how we also calculate the mean or expected value and variance and standard deviation for binomial probability distributions. I will be doing future lessons on the binomial probability distribution as well, but these are the fundamental principles to understand when you're computing probability for binomial distributions. And it is very important to recall, as I would have outlined in my first lesson on binomial distribution, how it is that we identify a binomial probability distribution problem. A binomial distribution problem is characterized by independence of trials, which means that the outcome on one trial does not affect the outcome on the second, third, fourth, or nth trial. While there is a fixed number of trials as well, and there are only 2 possible outcomes which we label as success, which is the occurrence of the outcome of interest to the researcher, and failure, which is the occurrence of the outcome that the researcher is not interested in calculating for. So these are the 3 main characteristics of a binomial probability distribution, and this question satisfies the conditions of a binomial probability distribution. Firstly, there is a fixed number of trials, which is 7 randomly sampled drivers are taken. Secondly, there are only 2 possible outcomes, because either the drivers, it is reasonable to assume from the question that either the drivers will come to a complete stop at the intersection or they won't. That's success and failure, and we're given the probability of success in this question. And the third condition is that the trials are independent of each other, because the question says that no other cars, when no other cars are visible. The experiment is carried out on the condition that no other cars are visible. So if no other cars are visible, then it means that the driver coming to a complete stop or not coming to a complete stop at the intersection has no impact on any other car coming to a stop at the intersection, either on the first, second, third, or fourth trial. And moreover, because there are no other cars at the intersection, no matter how many times we are sampling a car passing the intersection, the cars passing the intersection are individual cars that we're looking at. So no other car is at the intersection at that point. So it means that the occurrence of a car at the intersection, stopping or not stopping, does not have an impact on another car stopping or not stopping at the intersection. So we say each trial or each unit in the sample is independent of each other. They don't affect each other. So the conditions for the binomial distribution are therefore fully satisfied. Independence of trials or independence of samples, of sample units, and 2 possible outcomes only, success or failure, and there are a fixed number of trials in the experiment. All these conditions were satisfied, and hence the use of the binomial probability distribution is completely ideal for problems of this nature. So you can think of many binomial probability distribution situations in real life, such as, again, if you apply for a loan, you might either get approved or not approved. And we could take a fixed sample of loan applications. And so one person getting through for a loan application might not affect, in general, the chances of another person getting through for their loan application or being approved for their loan application. So there would be, if we have the conditions of independence of trials met, that there are only two possible outcomes and there's a fixed sample size or fixed number of trials, then we can use the binomial probability distribution. And that's it for my lesson on binomial probability distribution for now. I will be doing future lessons on this topic. Thank you. Hope you enjoyed this and hope you found it very useful in establishing an understanding of the binomial probability distribution and in your exam preparations. Feel free to like, comment, and subscribe and share as we continue this discourse in mathematics and statistics. Have a good one.